All right. So, any questions so far? No, we're good. We're experts at higher order functions and we love them and we hate for loops, right? Cool. How did workshop go yesterday? Yeah, we got some of it done. So the one thing that I didn't touch on that probably the first problem did, which was basically like, hey, return a function that does New York tax or New Jersey tax. And so that might have threw you for a little bit of a loop, which is like, how can I dynamically return a function? Did we figure it out? Did we get past the first problem? Yeah, just an if statement, right? So like I didn't explicitly show you how to do that, but functions, when you define them, they're variables. So we can use all the other code that we know. Like, hey, if they said state is New York, let's return the variable that is a pointer to the New York function. Or let's turn a variable that's a pointer to the New Jersey function. Or did anybody solve it without writing two separate functions? Okay, so I just want to show this real quick then. So this is probably what the solution does, where it will define like New Jersey function or New York function, function A and B, and hard code hard code in a bunch of sales tax down there. Is that how we solved it?
Yeah.
Do we have other ideas on how I can maybe do this by just returning one function always? Using closure. So instead, let me just get rid of function B here. This one kind of matches what the solution would have looked like. Obviously, I'm not doing the real business logic. But if we had something like return sales tax times price, when they actually call this thing, they'll give us the price. So the only dynamic thing that really changed between those two functions was like the sales tax. And yeah, I know there was state tax as well. But let's just pretend it's just sales tax. So if I was always going to return one function, how can I make that function operate differently based on the config they gave me? Any ideas? Okay, yeah, sure. We need some flow control. So we could use a switch statement or we could use an if. But really, the only thing that changed within those functions was the sales tax and the state tax, right? And so most of us probably wrote two functions that hard-coded those values. Instead, I want to return this function, and the sales tax could be one of two things. How can I make that work? I'm leaving this pretty open-ended to see if you come up with it. Well, we said, remember, there is no sales tax inside of function A, right? So where is it going to look? Yeah, it's going to look at its package of scope, right? The package that it got shipped out with. So that means if we have a sales tax up here, when we return function A, sales tax is going to actually find the value 10. Does that make sense? Because sales tax here is going to be in that little scope package that A will say, hey, when I got defined, I was also around another variable called sales tax and its value was 10. So now if I wanted function A to be dynamic based off whatever the state was, when you called this, what could I do? So right now, sales tax is always going to be 10, right? Right now, it's always 10. It's just hard-coded, make sales tax 10. So instead of switching which functions I wanted to return, we could instead do what? Yeah, so we could do yeah, but functionally it's going to have the same effect, right? So what he's saying is we could have instead done, so ternary looks like this. So there's no difference between line 13 and what goes on over here. It's just different syntax. But the thing that I'm trying to show here is that in our closure, we could have changed what the value of sales tax would have been. And so sales tax would get set to 10 or 7, whether we did it this way or this way. And whatever function we return out of here, sales tax would hold that value forever. Does that kind of make sense? That's just putting more of the concepts together from yesterday to have less hard coding. But it totally doesn't matter if you solved it the other way. Just figured I'd show you how this could work as well. Does not seem like we're too happy about this, though. Everyone dead. All right. Goodbye. So, today we go to recursion, which is the big monster that we've heard about probably before. It's this big scary idea at the end of sort of the beginning stage of programming. Because, to put it politely, recursion is a mindfuck. It's this concept where a function calls itself over and over and over again until it doesn't. And that's kind of a maze that our head has to step through to figure out what's going on. And we're going to get there. But this is a big topic, so this probably needs even more emojis. So real scary, big recursion. But honestly, the stuff that we did yesterday, conceptually, maybe not conceptually, but in practice, the stuff that we did yesterday is harder than recursion. Recursion is this big idea at the end of beginner programming because it kind of puts together all of the concepts that we've learned before. It's going to involve the call stack, which we'll talk more about today. It's going to involve scopes, nested scopes, functions with their own scopes. And then it's also going to involve, when we get down to it, working with data structures such as strings or arrays that hold infinite arrays. So here we have a number. Here we have an array that just has the number 2. And then over here we have this real ugly, I broke that. Nested array. And the only way that we'd ever be able to sum up all of the numbers inside of here is with recursion. So that means that we need to have a good idea of how to iterate over arrays. And so that knowledge comes back into play. And recursion is going to be the tool that lets us say, hey, if this thing is still an array, we need to go deeper. And if this thing is still an array, we need to go deeper and deeper until we finally get to a number that we can actually do something with. And so recursion actually isn't used as much in real life as you would think it is. Its biggest application is to traverse data structures that could be however many levels deep. And so a recursive solution would look, it would work for this, and it would work for this, and it would work for this if there were literally 1,000 arrays inside of here. It doesn't matter. That's what recursion allows us to solve. And so generally, that's the only time we're really going to use it in real life, because, and some people will grasp for recursion a lot more frequently than that, but there are some performance concerns with recursion that doesn't make it always the best solution. So really, the reason that we teach recursion and the reason it's at most interviews to get into a boot camp is because it really demonstrates a cumulative knowledge of all of the basic stuff that we've covered so far. In reality, you won't use it as much as we make it sound like it's a big deal, but that's okay. By the end of, I'm going to do this today, but by the end of tomorrow, we should definitely have a good idea on how to approach this. And if not, we'll practice a bit more. But by the time that you want to go to the interview with full stack, I'm giving you this freebie, you will have a question where you have to solve this. And unfortunately, you might hate me a little bit because actually, when I was here and I took this test, it might have only went 3 levels deep in the worst case scenario, like this one. And I didn't know what recursion was, and I got really lucky that I wrote 2 functions that called each other instead of themselves, but it only would have worked for up to 3 levels deep. And that was enough to pass all the test cases. And so, again, the test specs, just passing them doesn't matter. They're actually going to look at your code to evaluate what you actually know. And so whether you failed all the test specs, but your code demonstrates a good knowledge and a good understanding of problem solving, you can still get in. And in my case, I passed all the test specs, but if you looked at my code, I actually didn't know what I was doing, so they needed to check me deeper. And so because of that, they changed the test spec to not do this, but to do this. So you'll never pass the test spec without recursion now, and that's basically my fault. But that's okay, because we're going to learn how to do recursion, and you're going to nail that problem and the interview problems, and it'll be great. So before we get there, we're going to take a step back, and we're going to build up to this slowly. We're going to go over a few examples that I think are a little bit more practical, because one of the examples in the slides today absolutely sucks, and we'll see why later. So first, what I want to write a function, and this function is going to take in a number. Basically, we want to log out that number, and we want to log out all of the numbers until we hit 0. And when we hit 0, we want to log out liftoff. We're counting down basically till a rocket launches, and you tell us how long till a rocket launches. Does that sound good? How can we do that? We write a function. And what does it take in? And are we returning anything?
No.
Why do we say yes? So we're not at recursion yet. Definitely not yet. And I didn't say anything about an output. We don't want to return anything. The problem spec here says log out the numbers or log out liftoff and do both. I don't say anything about an output. So when we hit these problems on the tests for admissions or that we'll take on Thursday or for other coding boot camps, the first thing that we want to figure out when reading the problems is what are my inputs and what are my outputs. And they might not explicitly say return this value. They might not use the word return, but they might say we want you to end up calculating this or whatever they say. You have to translate that and figure out what they actually want to return. So make sure you definitely read the problem spec a few times to figure out what exactly am I taking in and what do I need to give back. Because in general, if we want to sum up a bunch of numbers, I've told you that before we dig deeper, it's really great to just set up this general structure so we don't have to worry about the return. Then we could just worry about the logic on when do we want to update sum. And it just sort of gives you a little bit of a structure before you've really solved the problem. And that makes life easier because it just removes some things that you don't need to keep in your head until you get there, so to speak. Like I've already handled the return. I don't have to think about it. Cool? All right, so that's not what we're doing. We said that instead, generally when we approach a problem, it's also good to sort of write out the pseudocode for what we want to do. So what do we think that is? And this is kind of like English. It can look a little like code, but in general, it's in English.
If less than 1 log liftoff.
Okay, that's one thing that we need to do. And the other, Yeah, so generally what you want to do is translate the specs into comments here, because it'll kind of give you structure on the whole problem, and then you'll have to go back to the spec. So, I mean, this is a simple one, and I have the spec right here. But still, that's a habit that you should get into, because it'll kind of keep you on the right path. But this actually probably isn't the way that we want to do it. So in this case, because logging out liftoff is the last thing that I want to do, my check instead is really if the number is greater than or equal to 1, we want to log number, and when that's done, we want to log liftoff. But this isn't enough, because what I really want to do is if the number's 10, I want to log out 10, 9, 8, 7, 6. And then when we're below 1, I want to log out liftoff. So how can I revise this a little bit? We could use a for loop. Does anybody have a maybe shorter way that we could do it? Besides recursion, forget recursion. It doesn't exist yet. Okay, now I think we're just complicating it. This is day one stuff. Okay, so I want to log the number possibly many times. So if we're not lower than 1, I need to keep logging this number. So we need a loop. And yes, a for loop would work, but a for loop introduces a bit more syntax. I got to worry about initializing some variable and some condition and some decrementer. And I don't really need all of that, so it's a little bit easier for me to just use a while loop. You could definitely use a for loop if you want to, though. So while the number is greater than or equal to 1, what do I want to do? But if the number started at 10, I need to log 10 first, right? And then, because we're in a loop, we have to eventually break the loop. So now we can decrement. Just like that. We agree? And so when we're testing our functions, it's generally best practice to start with a simple piece of data. So in this case, let's just check that when we call liftoff with 0, we get liftoff and nothing else. And now we kind of want to check the other code path. So generally anything that's 1 or greater. So when we have 1, we log out 1 and we log out liftoff. So let's test 1 bigger than 1. When we log out 2, that works. And now we can test it with a really big number. And it still works. So that's great. And let's just stop that. Stop. Okay. Yeah, it's very slow. So actually it's not, what's slow here isn't necessarily the for loop, but actually drawing this to the screen takes a bit of time. And so the actual drawing to the screen makes it a lot slower than just if we had a while loop that didn't log anything. Anyway, any questions on this? Do we feel good about this? We should feel kind of good about this one. Okay, cool. So this can also be done with recursion, which we're going to build up to and then refactor this in a second. But before we can get to that, we need to review the call stack and this idea of functions being able to call themselves. So before we get to that, I have this example here. So we've got 3 functions. And I want to know what happens when I call line 47. So take a second to follow that and try to imagine the order in which these logs are going to appear on the screen. We good? Okay, what do we think the first log will be on the screen?
Start A.
And then what?
Start B.
Okay, then what?
Start C.
Then what?
And C.
Then?
And B.
Yeah, that was actually pretty good. Whoops, let's get rid of that lift off. I think pretty much everybody nailed that one. So that's really good, but let's talk about the call stack anyway. So you can imagine that, let me see if I could demo this. That's too complicated. Well, so let's simplify it a bit. Let's imagine that when we run our whole program, that's kind of called main. And depending on your environment, sometimes you'll actually see that in the error call stack, there'll be something called main. But in this case, in Node.js, it's really this evaluation machine. And that evaluation machine is a function that's actually reading our code and deciding what to do. And so here we see when I just had that error, the evaluation machine got broken on line 46 because I had this stuff over here. So that's kind of like our outermost call stack, but we don't really care about that. We care about the call stack inside of our program. So main is running, it comes down, it basically, before the program runs, it would have defined all of these functions, right? We've said that functions, when they're declared this way, kind of in the nanosecond that you hit run, it will actually make all of these variables exist and make all of those functions exist, which means that I could call A up here, right? And that's called hoisting, yeah. So now we're at runtime. We're actually evaluating lines of code. There's nothing above here to evaluate. So the first line of code that we're going to evaluate is where? Line 30. And it says, hey, to evaluate a line of code, I need to solve whatever expression is there and get some value. Which in this case, we don't do anything with the value anyway, but it still needs to run function A. So now, I'm just visualizing that kind of the main thread. When we come down here, it's going to get paused on line 30. That says, I have some other work to do. And in this case, the work that I need to do is to run what? Yeah, we need to evaluate function A. And whatever function A resolves to will be the value that gets plugged in on line 30. So we kind of add A onto our stack. And that's how it keeps track of, now what I need to do is I'm going to move the cursor where I'm currently evaluating code. Where is it going to jump? Yeah, it's going to jump inside of function A. It's going to find A on the scope, say that's a function, I can run it. So I actually need to evaluate this stuff now. And so that's visualized by putting A on the call stack, saying, hey, I'm currently running A. And when A is done, I'm going to jump back to wherever I was. That's kind of review. I think we've spoke about that a few times. I think you're with me so far. So when we jump inside of A, for half a second, console.log is also a function that it needs to run. That'll get added on the call stack. It'll put start A out on the screen, and then this will disappear off the call stack, and it will jump back over here. Does that make sense? Okay, I'm not going to visualize the console logs anymore because they're just going to come on and off immediately. So start A will hop up on the screen. It comes over here and it says, wait, I can't go further until I resolve B. So what happens to my stack? And A is stuck where? Cool, so now we're saying we need to go finish B. And whenever we're done with B, we'll jump back to A at line 40. And whatever gets returned from B will be what we plug in right here pretty much, which I don't do anything with. So we hop into B, and we'll log out start B, which is what everybody said. We're going to see start A, then start B. And B says I need to go call C. So B is now paused. 47, thank you. And C is pretty easy. We log out start C, we log out end C, we hit that closing curly brace, and what happens? Yeah. And because I think you're grasping this pretty well, let's instead so when we finish running C, C returns what? Yeah, so it says, okay, I just got back 100. This comes off the call stack. Let me go to wherever I was paused and put in that value that I just got. And so we were paused on 46. That 100 value basically says we just evaluated C. We got back 100. So that's pretty much going to end up right here. And so we solved C, we plug in that value 100, we run this line of code, then we can log out end B. So B comes off of the call stack. What does B return? Okay, so undefined, thank you, technical terms. Yeah, so this line, B returned, we didn't return anything. So by default, B returned the value undefined. Undefined gets plugged in right here. We don't do anything with it. So we're done with line 39 now. And we continue. We log out end A. And we hit the end of function A. So A comes off of the call stack. And now we're back to the main loop, so to speak. So we jump back up here. Whoops. And this evaluates to what? Why? Yeah, nothing was returned out of A. And then so after that, we continue, and we would see done with functions. Does this make sense? I think usually I go more in depth, but it seems like we've grasped that. So if we don't have any questions, then we'll continue. Okay, so to demonstrate why functions are able to call themselves, we have this example. We have this function recurse. Does recurse have valid code inside of it? Why not? Well, the keywords doesn't matter. This is a variable, but that variable is not defined in recurse, and that's not defined on the global scope, right? But when I run this program right now, we don't have any errors. And that's because when the program first runs, it says, okay, I've got a function called recurse. I'm going to save a reference to this code, but it doesn't actually run that code. So JavaScript doesn't know that that's going to break. So instead, when I call it now, is the first time that it actually says, let's go run the code inside recurse. And that's when it finds out that this thing doesn't exist, and it throws an error. So the thing that I'm trying to demonstrate here is that functions will get defined before the code inside of them ever runs. So we see that ASD whatever doesn't exist. But actually, inside of this function, I can call itself. And that's a little bit of a head fuck at first, because we're like, how can we, especially while we're in the middle of writing this, like if I'm going to type this out and I haven't even finished the closing curly brace, it's really weird for our head to feel like, hey, it's going to be okay that I can call the recurse function. because I haven't even finished writing it yet. And now I finish writing it. And it looks weird because it's like, how can you call something within itself? But that's because there's those two phases. I can't ever call a function and invoke it until it's actually already been defined. Does that kind of make sense? Like when this first runs, it's going to define recurse. So no matter when I call it, recurse doesn't exist in the local scope, but it will exist on the global scope by the time I can ever actually run this. So it is valid to call a function within a function. Does that make sense? Yeah, so what I was trying to demonstrate is that when the program first runs, it's going to make a variable called recurse as soon as we hit line 26 pretty much, and its first initial go through. It's going to say, let's make a variable called recurse, and whatever's inside of it, I don't care about it right now, but make it available later. And so later is down here when I actually invoke it. That's the first time that I say, go run that code. And so by that point, when the head actually jumps inside of here to run, we have to have already defined this thing. So recurse does exist. I will be able to call it inside of itself. And that's like the first head trip that we have to get over and realize that that's valid. And it's going to seem weird when we code it because you're in the middle of coding the function. You're like, how can I call it? But it's about when we actually run it that there's the two separate phases. First, it gets defined. And so if we ever hop inside of there, well, it has to already exist at that point. So calling recurse will be valid. Yeah?
So does that mean you can't use like the arrow syntax if you're trying to do a recursive function?
So that's a great question. So I'm just commenting off the recursive call because I don't want to talk about that yet, but to demonstrate this point. This is valid, right? In this case, still, when the program runs in that nanosecond before it actually starts going line by line, it does scan for the functions, and basically, you know the visualization of it, copy and pastes it, right? So basically, it gets defined, which means I can call it before it looks like it got defined. And so this is valid. But in this case, when functions are written like this, they don't get copied and pasted ahead of time. It has to hit line 34 for real to actually give that arrow function to that variable. So when I run this, what's going to happen? Yeah, recurse2 isn't defined yet on line 33 because it hasn't evaluated the equal sign yet. So that doesn't mean we can't do recursion. That just means that if I write the function like that, I have to call it after the fact. So now, on line 39, when I first call it, well, it's already hit this equal sign, so recurse2 does exist. So when we jump inside of there, it will exist. So recursion will be possible no matter which way you write the function. It just depends when you call it. If we do the equal sign, we have to call it after the equal sign. And in the other case, we could call it before or after. It doesn't matter because that function will get saved before any lines of code actually evaluate in that evaluation machine. Make sense? Cool. So now forget arrow functions. We're not going to use them for the rest of today, maybe, hopefully, just to make things easier for you because you're more familiar with this pattern. So I'll try not to use them. So now, thinking about the call stack, let's just imagine it. In the main function, the first line of code that we're actually going to evaluate is what? Okay, besides actually making the function, what is it? Like, which line? 33. So when I'm talking about the first line of code that actually runs, I mean like real. And that's what I'm always going to mean. Just like we don't really have to think about the pre-phase where it defines the function. I'm not really referring to that. So here, the first line of code that it actually can evaluate is line 33. And so on that case, we were at main, but when we hit line 33, we're going to what? So we're going to add to the call stack this call to recurse on line 33, right? And now when we're inside of recurse, what's the first thing that happens? Yeah, we're going to see in recurse up here. And then what happens? And then it does this. And when we go inside of that call, what happens? Yeah, console log, we'll skip that one. What next? Recurse. And then what's going to happen? Forever and ever, right? So we might not have seen this before, but what do we expect about to happen when I run this? Come on, save us. Where's the error? Hello? We should have an error. It looks like it stepped in and stopped itself. But I think I did see a red flash. So let's try it again. There we go. So I just turned off the console log because it kind of bugged out and we lost this error somehow. But yeah. Anybody know what this is called?
Stack Overflow.
Stack Overflow. How many know what Stack Overflow is? Not in this context. Have we seen Stack Overflow?
Yes.
I hope that at some point in this course you have Googled something and ended up on Stack Overflow. Definitely don't hesitate to Google things. If something's not making sense, or even if you got the answer right, but you want to know more, Google. That's the biggest way to augment your knowledge. And Stack Overflow is great, and that website was named after this. So basically what happens is, remember we spoke about those scopes, the closures, and this call stack here. This takes up space in the computer for it to keep track of, hey, I was stuck at line 33, and this was my closure. And even to put something on the call stack, it is represented as an object, and that takes up space. So actually, if our call stack gets really big, which it did in this case, it probably went to like 25,000 times, we run out of memory. And so thankfully, the JavaScript interpreter steps in and says, I don't think you meant to do that. I'm going to delete everything and give your computer back to you. Because if that didn't happen, you would not be able to stop the program at all. Your computer would be completely locked up. So here we've demonstrated recursion. This is a recursive function. That's all there is to it. Recursion is being able to call a function within itself. But obviously this isn't a practical example yet, because this doesn't even fucking run. But do we feel good about the visual of what happened on the call stack and why we ended up with an error here? Cool. Any questions? Because that's honestly the hardest part, is that we can call a function within a function. And now the rest of the lecture, we're going to focus on like how to actually make an algorithm in here that will do what we want. Yeah, Z.
Yeah, I'm kind of just randomly curious. How is this stopped the first time?
What do you mean?
Like when this thing first happened to the first person that this has happened to?
Yeah.
Like how did they stop this? It actually just runs
So that's a great question. I would imagine that the first developer that tried this did have an idea of what would happen and they built this error beforehand. But if they didn't and there was no way to catch this in like the language itself, then the computer would have completely frozen and they would have had to get it to turn off and turn back on. You can demonstrate this in a web page. If you've ever seen the spinning wheel and the website's completely stuck, something like this might have happened. And I mean, okay, we'll demo it. So if we just go to, whoa. No, actually, I think their engine's good enough to catch this. Yeah, it didn't break my browser. But sometimes I'm able to completely break this or break REPL and get the spinning wheel. But then we'd have to force close everything anyway, so we don't want to do that. But yeah, I'd imagine that the people developing this know more than a beginner programmer, so they made the safeguard first. But I'm sure back in the days of binary machines, they completely crashed some of them. Anyway, good question. So let's go back to liftoff. What? So what I want to do is basically we have a function that takes in a number. I want that function basically to say, hey, if the number, I don't want to give it away yet because I think that you're kind of catching on. So does anybody have any ideas on how we can recurse? Basically, what was the problem down here? We forced it. It always calls that same function, right? So in recursive functions or solutions, there's always going to be what's known as two paths. One is the recursive case, the path that will actually call itself again. And another one is the base case, where it's not going to add onto that stack anymore, but it can actually return. And so like pretend that this call down here actually returned, then we go back to the one before, right? And when that one returns as well, we can work back down and get out of the call stack. So with that in mind, any recursive problem is going to have at least two paths. One, which is actually going to call itself, and another one that's not. So I'm being pretty open-ended here. If we look back at our logic up here, what do we think is sort of our condition that we could use to determine which path we want to take? Okay, so number minus minus isn't a condition. But I know what you mean. And so no keyword like wall. What is the actual thing, the expression that we care about? Yeah. If the number is greater than 1, what do we want to do? Okay, so let's start slow then. Let's leave the recursive case open for right now. And this is generally the best way to approach these problems, is solve the base case first. So we're having a little check here that if the number is greater than or equal to 1, we're not going to do that yet. So let's instead handle when the number is 0. What do we want to do? What error is going to happen if I call a countdown right now? How do I define it? Yep. Oh shit. This one is still here. Okay. What's going on? See, in this case, I think we actually did break their back end. I'm not getting like a new prompt and I can't stop the program. So we broke something. So we just need to reload the whole page. Hello? Okay. Cool. So generally when we're approaching recursive problems, we want to solve the base case first. And we're going to get a lot more experience in this lecture on base cases and recursive cases. But base case is the code path that doesn't result in adding another call to the stack. And so we want to figure that out first and then test it. So we call countdown with our base case, which is 0, and we see that it logs out liftoff. There's no crazy call stack or anything at all, and that's great. Are we on the same page for what we have so far? So now what we want to do is our kind of tasks for this problem, where if the number is greater than 1, we want to log out the number. And we want to continue doing that while the number is still greater than or equal to 1. So let's just handle this task first. And test it with a number. We log out 1, we log out 10. That's great. So we have a function that takes in a number. And if the number is greater than or equal to 1, it'll log it out, else it will log out liftoff. The step we're missing is that we want to do this for every number between the number we took in and when we hit 0. So right now, if I have a function that takes in a number, and it'll log out the number if it's greater than 0, else it'll log out liftoff, that's kind of what I want to do inside of here, right? So why don't I use the same function that we already have? What does that look like? So I've logged out the number. Now what do I want to do? Yes, exactly. So before I demo that, let's just think about if I call liftoff with the same number that I have right now. So when I call this thing with 3, and we have our call stack. Liftoff with 3 is going to do what? It's going to say, hey, my number is greater than or equal to 1, so I log it out. And then what does it add to the call stack? Sorry, it's countdown now. Yes, it's countdown now. You're correct. So if we call countdown with 3, right now it's going to call countdown with 3 again. And when we call countdown with 3 again, what does that one do? It calls countdown with 3 again, and we're back to the same problem we had before. Yes. So it's easier. Just get rid of this one. It's countdown. On the actual admissions assessment, it's called liftoff. So I've said this so many times that I'm used to liftoff, and I'm confusing you. I apologize. So yeah, we see the problem here right now. We're just going to log out a number. We're going to call the same function that's going to do the same thing, log it out, call the same function. So in general, anytime we're in a recursive case, when we recurse, we need to do something that will ultimately get us closer to breaking that condition.
We need to give number -1.
Yeah. So let's decrement the number, and let's pass the decremented number to the next call. So what actually changes down here now? We first call countdown with 3. And that one is going to do what? That one's going to call countdown with 1, and that one does what? What's that? Yeah. So when we finally call it with 1, it calls another version of this function with 0. And that one says, hey, I can log out liftoff. And at that point, when we call it with 0, what happens? We log out liftoff, and that function returns what? Undefined. And we go back to whatever's at the top of the stack, and we say, hey, in this call, my number was 1. We just resolved the countdown of 0, so I can continue from line 26. And there's nothing left for me to do, so I return. And this one drops off the call stack as well. And then this one. And then the original. Fuck. So, little.
Why is it minus minus in front of none instead of after?
Yes. So we've seen minus minus num, and we've seen num minus minus. We've seen plus plus num and num plus plus. They both will increment a variable. Now this isn't too important. It's going to come down to if you know it or not and how you're going to use it. But basically, if we do minus minus num, it means decrement the number and then give me the decremented number. So num is now 9. But when we do num minus minus, it says basically give me the current value of num and then decrement it. So over here, seeing num minus minus still gave us 9. But if I look after that, num is now 8. So I kind of just blindly listened and didn't demonstrate this. This would have been safer if we wanted to do minus minus. Whoa. In my case, I actually passed the current value and then decremented it after the fact. So we still had a maximum call stack. If this bothers you, don't worry about it. It's not that important. And again, most don't know the difference here. They just pick one and always use it. It's just that if you do it after the fact, you have to be aware of that. So generally, if you don't care, just do the plus plus or the minus minus first. And I actually think that's more readable anyway. The reason in for loops it doesn't matter is because, so I'm just going to leave these blank. So over here, we say, give us I, and then go increment it. We don't really care what the value of this term evaluated to, because by the time we go inside the code block, I would have been updated. So it doesn't matter in the for loop. But in the case that I actually passed in num minus minus, I did pass in the old value before it got decremented. So it's not too important. I would say just go with the plus and the minus before the number, and you never have to worry about this. Or more explicitly, do it on its own line here. Just let's decrement number, and then let's call countdown with the now decremented number. Okay, so this is real basic recursion. Do we have questions on this one? Cool. Ooh. Okay, so I added one more console log here. Try to think when I call this with 3, what will be the order of the logs that we see? I'm leaving you kind of open-ended still.
It's going to call every number. After every number, it's going to log that sentence.
3, 2, 2, 1.
So when we call countdown with 3, we're going to log out 3, and then we're going to call countdown with 2. And this one is going to immediately log the 2 out on the screen, and then it's going to call countdown with 1. So I'm just going to move this to 2 actually, so we don't have to do all the examples. When we call it with 1, we log out the 1. And when we call it with 0, what gets logged out? Liftoff. And then what? So in the call to 0, we log out liftoff. Is the function done yet? Yeah, so in the function with 0, it logs out liftoff, and then it says, hey, my number was 0, I'm finishing. And so actually, when we go back to this one, each of these functions has their entirely own scope. And that's one thing that's tricky about this as well. So if we take a step back for a second, when we first called countdown with 2, the number was equal to 2. And we logged 2 out on the screen. And then it said, let me go decrease my number by 1. So it lowered its number to 1. And over here, I'm representing the scope inside of each of these calls. So countdown started with number at 2. And then it decremented its 2 to 1. And then it said, let me call countdown with num. So we add this call to the stack. And that call says, hey, my num is 1. And then it decremented its number. And then, so number became 0. And this one gets paused. And so on the call with 0, number came in as 0. We logged out liftoff. We logged out our num is 0. And that one dropped off the stack, right? And when we hop back to these lower functions on the stack, does the scope visualization here now help make sense of why this looks like this? When we come back to the call with 1, its number was already decremented to 0. And so when it hits this line that says it's no longer paused, it did this, it skips the else, and it says, hey, my call with 0 is finishing. That's why we had 2 zeros up here. So this visualization is a little bit easier to see if I changed it like this. Is that a little bit easier of an example? So rather than actually change it in the scope, we can now see that the call with 0 was the first one that logged out liftoff and say, hey, my call with 0 is finishing. And then when we jump back to that other countdown, it was initialized with its number at 1. So even though we call countdown with num minus 1, when we come back, the number is still 1. We didn't actually update that number. And so it still logs out, hey, the call with 1 is finishing. And then finally, we clear that off the call stack. And now this one is unpaused over here. It skips the else, and it says, hey, when you called me with 2, I'm now finishing. And that comes off the stack, and we continue down here. So what's really important about this is sort of that inversion of the call stack. We worked our way all the way up, kind of doing this first half of the function. And then as soon as we called it with 0, the call with 0 is really the first one that ever finished. And as soon as the call with 0 finished, we go back to the call with 1, which was paused on 27. And then it says, hey, my call with 1 is finishing. And it returns. So the call with 2 is unpaused. And it does the same thing. It skips down here and says, hey, my call with 2 is finishing. And then we return back to the main global scope. And we can say, hey, all of them are now done. Does that make sense? Could we kind of get how that call stack built up and how they come back down? The call stack, are we good on the call stack there? Yeah.
Aside from the console log spitting out like unexpected numbers, is there a reason to use -1 over your decrement or like to?
Yeah, so actually the decrement wasn't, I mean, it's perfectly valid. But the decrement wasn't a good idea in the sense that inside of here, we don't really need to change number because we're not doing anything with it later. We just wanted to start a new countdown with a lower number. So this kind of makes more sense, and you see that it's actually a lot clearer to track that way because we're not using a decremented number at all, so we didn't really need to decrease it. We just needed to make sure we passed in a decreased number. And so here, this will evaluate to a decreased number. You could write it whichever way you prefer if you're not using that number inside of here. But I think that this is probably the best and simplest approach to this problem. And this log here makes it a little bit easier to follow. Because I know that even I got confused for a second because I don't usually write it like this. When I saw the 2 zeros, I was like, But then when we traced the call stack, it made a little bit more sense. So if we understand how the call stack builds up and builds back down, does that make sense? Because then the second part that I haven't spoke about is that it looks kind of weird. Like you kind of look at this and you think, well, when we call countdown with 0, aren't all of the nums now 0? Or maybe you didn't have that thought, but some people do. But the point is, every time we call this function, they're in their entirely own scopes. And so, yeah, the variable name is the same, but like they're all totally separate, and they're not actually sharing data at all. That's why when we come back to the call with 2, this number is still 2. All of the nums inside of these functions are completely separate. Each function keeps track of its own scope, even though it's kind of the same code that actually ran. And that's like the third head trip with this. 1, functions can call themselves, which is weird. 2, how the call stack builds up and then builds back down, the sort of inversion that we see here. That 2 was the first one to run, but the last one to finish. That's the second really confusing thing. And the third one is that all of these numbers are totally separate. Those are the 3 really big stumbling blocks when learning this concept. So do we have questions on those stumbling blocks that I could explain better? Yeah, Z.
So obviously, like each time it's run, it basically has its own functional scope.
Completely own functional scope.
But in that sense, because this is like one function, like that functional scope kind of gets destroyed by the time it's finished, anyways.
I'm not exactly sure what that question means, but it's like when the call with 0 finishes, yeah, that run destroys its own scope.
Okay.
But the others are unaffected because they're still running.
Right, but once the entirety of the recursive function is finished running, then the scope of all the numbers they basically self-destruct.
So don't think of this as one big function. It's really one little small function. And that small function just runs a totally different small function, even though it's the same code that they're running. And so as they come online, they make their own scope and say, what did I get called with? Oh, I got called with 1. My number is 1. And when I'm done, I delete all of that. It has no idea that there are other functions above and below it in the stack. Do we need a visualization of that? The different function scopes, or do we kind of get that? Yeah. Did this one, should I get the whiteboard? Did this one? Does this help a little bit? It's like everything on the stack keeps track of when it should run based on its position in the stack and where it was paused, but they also hold their own scope. So when we jump into countdown with 1, it still remembers that its number is 1. Yeah.
Yeah, so going back, so like say if one of the scope, right? If this recursive function, for example, if each step along the way it returns and stores value, then that would mean that all the scopes are preserved by the end of the function?
So it's like as soon as countdown hits the end curly brace,
Uh-huh.
this is all completely gone.
Okay.
They really have nothing to do with each other. It's the same as if in here, each of these took in a variable called num.
Right.
Like every time we call one of these, it really has nothing to do with any of the other ones at all.
Okay.
It's like we really got to think of them as kind of totally individual functions, even though, you know, they're calling the same code. Every time we call that same code, it makes a brand new scope. It's not really aware of anything else.
But the thing is, if it does return a value, right?
Yeah.
If countdown returns a value, then that value, say if you're trying to count down from 3 to 0, so I know that the function 3, when it's calling 3, it has its own scope. And
Yeah.
then when it calls the number 2, it has its own scope.
Yeah, yeah.
But by the time that 3 gets returned, it's preserved in a new scope or its own scope.
It'll, like, if countdown 0 returned a value and we saved it, we'd save it in the scope that called it.
Okay.
And that's the final hardest part of recursion, is what if these functions return values? So we will do that now as well. Yeah.
And this only happens in recursion, where you have a scope on each number having your own scope.
No, this is how functions work. So let's go back to this one. So in this case, let's follow the call stack here. We're going to call function A with the value 10. What gets logged out on the screen? Yeah. So A has a local scope where its number is 10. And then it calls B with num times 2, right? So it looks on its scope, it sees, hey, my number is 10. It does 10 times 2. And that value is what that we pass to B? 20. So in the call to B with 20, we say, hey, in our scope, our number is what? 20. And what does B do first? It logs out what? Yeah. And then B says, I'm going to go call C with what? Because over here, if we didn't see that, when I call C, I'm passing in num times 2. And so in C, C's num is 40, right? And then we see NC, and C returns what? 80. So this one, B, was basically paused at line what? It was B was paused right here, right? Yeah. And it was paused basically trying to evaluate what the call to num times 2, what the call to C was with num times 2, which we just said if our num was 20, we called C with 40. So we're paused trying to evaluate what this is. And C returned what? So now, basically, this plugs in 80 right here. I mean, I'm blending the scope and what line was evaluating. But we get an 80 right here, and we'll see the result of C was 80. So then we log out end of B, and we don't really return a value, but this drops off the stack. And so when we run this, that's again that same order inversion of the call stack. And each of them have their own scopes, even though the variables are called the same thing. So all of those concepts is exactly the same in recursion. The fact that it's the same function doesn't actually change anything. The only difference is that with recursion, we need to have what? We need to have a stopping point. We need to have a base case. That's really the only difference. But a bunch of functions calling each other worked exactly the same way. No. Okay, questions that we can go deeper on this. Okay, let's take a, yeah.
Well, I have a question. What if you have a counter in a function, and so you have to define the counter as like a number, so you start at 0, and then you use recursion, and every time you recurse from that function, it redefines the counter at 0, right?
So it doesn't redefine the counter in the other scopes. Like if in here, every time we call a countdown, they'll have their own variable called other num, and it's set to 10. And every single time they also define some variable called num. But defining this num inside of the call with 0 doesn't go back to the other call and update its num, which is what I think you were getting at.
I mean, I guess if you're just, I'm just thinking if you're trying to keep a count of something.
Yeah,
you
so
have to define it.
if we wanted a count of how many countdowns got called, then yeah, every single countdown is going to be 1. So instead, and yeah, that's because each of them have their own functional scope, so they're not aware of what the other ones did. So if we wanted them to all,
Make it a global variable?
yeah, let me move this up here. Is this what you were wondering about?
Yeah.
Yeah. So in that case, yeah, if we needed some data to persist after one of the calls, then it has to live in a higher scope. If we were trying to track how many times countdown ever got called, then yeah, it does need to live on the global scope, because each of them would say, hey, I just got called and I'm 1. So if we need to aggregate, that's when we move to a global scope. And that's why sometimes it's okay to use the global scope if this is the functionality that we're looking for. But now this also means if I call countdown on another line and I call it with 5, the very first time I call that one, call count is already going to be at 3. So it depends. Are we trying to aggregate all calls to countdown ever? That would be okay. But if we're trying to figure out how many times it got called this one time that I started this process, we'd need a higher order function and closure. And because you guys are not too happy right now, we're not going to do that because that's adding another layer. But that's yesterday's knowledge coming into play. So I would instead, okay. So this is really hard because this is now combining yesterday's lecture with today's lecture and basically saying we need a new call count for the function that you're going to get. And it shouldn't be global. It should only happen for like the one time you call countdown. So in this case, we'd have to define a function out here. This I see some of your faces. This is a lot harder of what just happened here. But basically, I wanted a version of Countdown that will have kind of its own call count to worry about, which meant that it can't be on the global scope because that'll aggregate everything. So instead, when you call this function, it will make a count, then it will define a function here because this countdown has closure over call count, right? So then, and I know you haven't seen like this syntax, I defined countdown, then I immediately called it with the number you gave me. It's going to do that whole recursive problem we just spoke about, and at the end, we have a call count that only worked for this one time. This is a combination of today's and yesterday's lecture, and this is definitely harder than what we're trying to achieve right now. So don't worry about that, but that's a great question. And yes, the next step that we want to go to is how to return numbers so that we can actually do some work. Because this is pretty stupid. It's just logging things out on the screen. It's pretty useless. But I see that we're very tired, so let's take a 5-minute break, and then we'll go to making this more useful. And don't worry about this at all, but if this made sense, that's amazing. No worries.
Do they have standing desks at Bloomberg?
We do, yeah.
Yeah.
They work just like this. They're nicer though. Got 2 monitors. I never stand, but yeah.
Just hair?
What's that?
Just hair?
Just chair?
Just hair, I said. Meaning
Yeah.
hair.
Yeah, I mean, you can't like teach and sit, and because I get up all the time anyway, yeah, while I'm teaching, I'll stand. But it's probably like less than 3 times I've actually stood at work, and you really should because it's better for your posture and your body or whatever. But yeah, I sit and I dance, so there's my workout.
It's an interesting point because it might be good for your posture, but it also is uncomfortable. So, right, because now your body's and it's trained. So, how are you mentally?
Yeah, some people definitely prefer standing and think that it gets them more in the zone.
Right.
And I could see that because sitting can make you sluggish, especially if you're doing it for 8 hours a day.
Right.
And they do try to encourage people to stand. There are all these like videos about like your health and how to have correct posture. Yeah, I do not have good posture at all. I don't mind standing here, but at work I sit.
Maybe you'll start a revolution.
Of sitting,
Of standing.
Of
You know,
stand-
like you stand.
go back and just start making people stand. This is the stand-up hour. Everybody stand.
Sometimes it has that effect. Like one person stands and the other person stands, and like before you know it, the whole team is standing.
Yeah, the times that I've stood is most likely because the person next to me was standing. And I was like, oh, good idea. But yeah, I don't like it that much.
Yeah, that's fair.
Maybe if I start feeling unhealthy, I'll do it more. But
Do you listen to music when you vote? What kind?
I'm all over the place. So I go through phases. I'll go through phases depending on the season of what I listen to, and then I'll binge listen. So like I've done like a whole Kendrick phase where I just listen to his whole discography. Sometimes in the spring I go back to like high school phase, so like alternative music. What is on that playlist? We're like Taking Back Sunday and like other bands like that in the spring sometimes. You can make fun of me a few months ago when we saw what is it, A Star Is Born. I listened to the soundtrack of that while I was coding. So literally like anything, and then that's just my phase for the week. So pretty much anything. Yeah, I should go back to a rap phase I'm feeling right now. Yeah, right now it's a little bit more punk.
So throughout your workday, you don't have to like get on the phone with UX designers or anything.
I absolutely hate the phone, and when it rings, I freak out. So there's one product that I maintain that's absolutely terrible. But you can imagine that because we have all these circuit pipes, right? Like we buy a circuit from Verizon. They install a pipe that connects Tokyo and New York. Well, Verizon, we bought it, but Verizon will maintain that for us. So they'll send us emails and say, this circuit with this ID, we're taking it down on this date between this hour and this hour. And we have hundreds of vendors. So it used to be somebody's job to read all of those emails and like do something internally to be like, hey, when network outages go down on this day, it's okay because that pipe, we know it was going to come down, so we should reroute traffic. But so like a big application is to parse all of those individual emails and instead create those alerts automatically. And so technically it replaced the job, but the person whose job it was, they got moved. I didn't get anybody fired for that. And so then like my app will also say, sometimes, they type gibberish and I couldn't find the details that I'm looking for. So a communications rep needs to go read the email and make the alert manually. And so when those emails fail a bunch of times in a row, this guy will call me and be like, why did it fail? And I'm like, they changed the fucking format. Again, I told you if they lock down the format, we can do it automatically. But if you have a human that's typing differently and they put a typo there, I can't code for that. And so anytime he calls me, we laugh about it and I hate it. And he'll always want to talk to me like for 15 minutes about like the Avengers or whatever he's hyped about. And I don't want to talk on the phone. I hate the phone. So here's my worst nightmare. And call me all the time. Yeah, I wake up in the morning, I see an email from him, I know it's going to be a bad day. Because also those parsers suck. They're written in Perl, which is the ugliest language that I've ever seen. Perl.
It's with a lot for statistics, right?
Look at this. This is very similar to the parsers that I write. And every variable has some type of symbol in front of it. A $sign basically means it's a primitive. It's going to be like a string or a number. And an @ means it's going to be like complex, like an array or an object, which I don't see any on here. They're all primitives. Oh, here you've got one. Like, what is this? This is a keyword of the language, and that's not readable at all. So this is a terrible language to work with, and you can imagine that there's hundreds of these patterns inside of the parsers. It was absolutely terrible project that was started before I joined the team. And it's kind of like hazing that the newest member of the team needs to maintain those parsers. So 120 different parsers, and each of them has their own code to connect to the email outbox and to write to the database. But all of them really need to do that. So that should have been centralized. Because when we change the database or the email, 120 of these scripts need to have that updated. And it's a real big problem because I can't, without a lot of time, I can't centralize a lot of stuff that we'd want to know. And so that's a big pain in the ass. And I hate that project. And the guy who has to deal with the output calls me all the time. Nobody else really calls me. we'll do more like video calls. But all in all, like my time is too valuable to spend talking to non-coders. And it sounds really fucked up, but it's true. And so like my manager, when I first started, like I had a problem. He was telling me, be more of an asshole and hang up on them and get off of the phone. And like so slowly I've had to be colder to this guy so I get called less. Because I don't want to sit and talk Avengers with you for 15 minutes. Like I'm sure it's great, but I've got stuff I need to do. You kind of just read my output. You don't have much else to do, but I do. So I sound like an asshole, but it's true. Anyway, yeah, if you like talking to people, you can still talk to people as a developer. It really depends on the culture that you're going to. I want to be in a role where all I do is code and I listen to music and I don't talk. But there's a mix. It depends where you join, and that's what you'll figure out in the interview phase. Although most of you are probably like, I just want a job, just get me a job. And then you'll figure out for the next job what you actually want to do. But yeah, this is Perl. It's absolutely terrible.
The title is Perl, the most hated programming language, I guess.
Okay, so good. My evaluation of this language is correct. And PHP is also an ugly garbage language. And this is what most of my team had wrote in before I came in and brought in all of the JavaScript stuff. But yeah, you see, JavaScript is a lot more readable. And when we do functional programming, we can make it even more and more readable. And functional programming here is really, really hard to do. But you hate functional programming right now because you don't fully understand it. But I promise those features of JavaScript make it awesome.
What can you use as a replacement to PHP? Can you just do JavaScript?
Yeah, so one thing about PHP is like, I don't know if you know HTML at all, but in PHP you can basically have a script that when you run it, it returns like, it'll like send back to the front end, here, draw this box and put in the username. So like PHP calculates what the front end should look like from the back end by like string interpolation. But in JavaScript, we can do most of this stuff on the front end and instead have a function that'll go talk to the back end and get the username. So it also means we offload more of the work into your browser rather than my server needing to process this for all 1,000 of you that want this like div. Anyway, anything you can do with PHP, you can do with JavaScript, but it's going to be more codey and less templatey, if that makes sense. But that makes it a lot more flexible. PHP isn't like a persistent server. It's like every time we run a route to get this, this would really like run a script called like hilarious tart conversion. But in JavaScript, it would hit like a program that's always online and says, when they hit this, I should do this. So they're different. There's pros and cons to both. But honestly, the syntax of PHP is problematic, and the functions are a lot uglier, and the syntax doesn't make as much sense. Like, so here, this says go to the array, and again, these dollar signs that are so ugly. Go to array A and push in these values. And just like the order of this, I don't know, in JavaScript, it's a lot more readable to say nums.push1. This like is a little bit harder to figure out what exactly we're pushing and where does it go. And so I hate just the signatures of all the functions inside of it. Functional programming isn't as great. I could go on, but yeah. Don't worry about it. There's a stigma against PHP. Unless you want to do WordPress, there's no reason to become a PHP developer. But once you learn JavaScript, it's really easier to pick up other languages as you go. The first language is the hardest because it's learning all of the actual concepts we spoke about today. Then when you learn a new language, you just have to learn what's different about it. What can I do? What can I do? But call stack is going to work the same way. Scope is most of the time going to work the same way. And so you don't have to relearn everything. It's just like, what's the difference between the two? And that's also why it's not a good idea to learn two languages as a beginner, because you don't know enough to really know the differences between them, because it really isn't just a one-to-one syntax shift. Good questions. I think we got everybody back here. So we can forget that last example with the call count, but that's great. Now we're going to go to some more practical examples where we are going to return values. So let me just preface this that it's already 8:20. Today might be very long, unless you just want to hop to the workshop and try it. but I do know that tomorrow's lecture shouldn't be as long and you'll get a lot more time in workshop. So let's at least definitely cover this one example. And then depending on how we feel, we could do 2 examples that are closer to what the workshop will ask, unless you feel like you just want to give it a go. So I'll ask like clarifying questions to see if you think you have the idea. And honestly, the slides kind of suck, so maybe we could just skip it. But we'll see. It's how you feel, because today is pretty long so far. All right. So we want a function that's going to take in a number, and at the end, it should sum up all of the numbers between that number and 0. So if we think about that, our control flow is pretty similar to the last example that we did. Plus this last example is in countdown liftoff. Plus this added spec where we need to add up the numbers. So first, before we do it recursively, what would this look like with a while loop, iteratively? Okay, so first we need some sum, right? And we're assuming that this is only going to take in positive numbers or 0. So what do we want to do? What is kind of our... So I'll be explicit here, but going back to tie some concepts together, would this also work? Why? Negative numbers are not falsy, by the way. The only the only falsy number is 0. The only falsy string is what? Yeah. So while num would also work. We're assuming we only get positive numbers, and so as soon as a number is 0, that would break. But yeah, let's just leave it explicitly there. So we've got a number. What do we want to do with it? So again, when we're testing functions, did I leave something commented? No, their backend is just slow now. Oh, thank you. You're right. The backend isn't slow. What's going on behind the scenes right now? It's going on forever. Yeah, what do we have to do? There we go. So just to tie in before, we could have been cute here because num minus minus would actually give the current number to sum and then decrement it. Like that's why if you know the shortcut, you can get cute with it. But seriously, don't worry about that. Let's just be explicit because explicit is better. So we're saying take the number, add it to the sum, and then decrease it. So it works for 1, it works for 10, it works for 10,000, or whatever I typed in there. And we see here, actually, that when I just ran it with the bigger for loop, that was really fast, right? So before, it really was that console log that made it visually slow. Okay. So in general, when we approach this problem, we want to figure out when do we want to recurse and when are we basically good. Okay, so if we've hit the base case, what is our sum? What should it be? Basically, when we hit a base case in this problem, we have nothing to add, right? So what's a good Hey, I had nothing to add. Yeah, so we could be explicit here. But I want to leave it as this for a second. So really, what do we want to calculate here? We've got a number, right? And we know that we need that number in our sum. So we definitely want to add that number in. But then, what else do we want to add? The sum of all the numbers below, right? So I'll just give it to you because we haven't done one of these before. So in general, as soon as we write this, we want to test it with the base case. So when I put in 0, I expect to get back 0, which I did, right? So let's think about what happens with 1. When we call this with 1, we're basically going to come down to line 145, and we're going to say we need to calculate our current number plus the sum of all of the numbers below this number, pretty much. The minus 1 is important because it gets us closer to what? To the base case, yeah. So basically, right here, we can plug in that we know that our number for this call is 1. And what we want to solve is 1 plus the sum of the recursive function for 0. So that's kind of like half of the order of operations there. Does that make sense so far? So we add on a call on the stack that says, hey, go solve what is sum recursive of 0. And when we step in and num is 0, we ignore this bit up here, right? And we return 0. So sum recursive 0 evaluates to 0, and then that comes back down to right here. And then we add those two together. And now that we have a single value here, we can return 1. And that comes off of the stack. And we see that when we call sum recursive with 1, we get back 1. So we kind of just made a big jump to the final step of recursion, which is how to return numbers out of functions. And this one is pretty short. So basically, the first thing we had to figure out is what do I want to return when I hit my base case? Because this will basically be the first thing that's going to start getting added together with everything above. So what happens when I call this with 3? Does this make sense on what the path is going to be and how the call stack builds up? When we call it with 3, it says, hey, I need to return 3 plus whatever the result of calling with 2 is. And we get stuck. And we say, well, we got to figure out what is the result of calling with 2. And that says, I need to return 2 plus calling this function with 1. And that one says, I need to return 1 plus calling it with 0. And now, when we call it with 0, this resolves to what? This resolves to 0, so this drops off the call stack, and we get back that 0 here. That's where the return value comes back down. Does that make sense? That's like the hardest concept to understand here is when we return, we go back to the last thing that called it, and we plug in the return value. And now this one says, hey, I can return 1 plus 0, which is 1, and I give it back to whoever called me, which is back here. And so I can return what? 3. And when I drop that off, I now return 3 plus 3, which is 6. And that's basically 3 plus 2 is 5, plus 1 is 6, plus 0 is 6. It's just sort of inverted in how that actually happens. We have to go all the way to the base case to get our first value. And then that one kind of bubbles up the stack.
So we should always think about returning the base case.
100%. When we're dealing with recursion, always figure out what is your base case and test it with the base case. Because then it becomes a little bit easier to figure out what do I have to do recursively. And so to figure that out, we just go one higher than the base case. Like in this case, we started with 1. And if we're thinking in our head, we know that we have to return 1, which is basically 1 plus the sum of 0. And 0 is what we chose to be like our final stopping point. So I think I can rewrite this in a way that makes it a little bit easier to understand, maybe.
So the base case here is 1, or is it 0?
What's that?
So is the base case here 1 or 0?
The base case for this is what? What's the only number that we hit this path down here? 0, yeah. We're assuming positive numbers to simplify this. So I'm just rewriting this down here without doing the return in one line. Does this version down here, does it work for our base case? So think about for a sec. Yeah, I don't explicitly have an if-else. But when I call this with 0, what do I get back? 0. So yeah, there won't always be a straight if-else. We can reorganize these things a little bit differently. So yeah, we test this with 0. We say let sum equal 0. We don't do anything else. We return 0. That works. So now let's run that. We get 0. Let's run that with 1. We get 0, which is incorrect. So instead, any ideas on what we could fill in here? We need to update the sum, right? Is that it? So that's another way to look at it. The same call stack buildup is going to happen, that when we hit the recursive cases, we're going to pause here. And then whatever the result was, we're going to add it with the number into our sum. And again, each call to sum recursive will start out at sum at 0, and then we'll really get the result of what happened later on and add it into its sum, and that's how they aggregate. Should I visualize the scope for this one? Or do we feel comfortable that all of the sums are different? They're not resetting all of them to 0. So we didn't need an else statement. That's the thing. Like generally it's easier maybe to do if else to separate the base case and recursive case, but it's not a hard-coded rule that you have to do it that way. You just have to basically, if we aren't greater than 0, we're not going to do this recursive path. And if we are 0, we just return immediately. So there is still a base case and a recursive case here. It's just less explicit. Another thing, what changes if we say let sum equal num and return sum? Does that still work for our base case? For our base case, if we pass in 0, does this work? Okay. And if we pass in 1, sum will be equal to what? So then what do I probably want to do in here if num is greater than equal to 0? What else do we still need to do? Yeah, but what changes in this case? What do we... Compare your answer, Z, with what changed on line 154. We already added the num into the sum, right? So what do I still need to add to the sum? So here it says whatever number we take, let's start that as our sum. That'll work for 0, it'll work if it's 3. And then we say, well, if our number was greater than 0, if it's 3, I still need to add in all of the numbers below. So when we call it with 2, the call to 2 says my sum is 2. I need to wait and get what the sum of 1 is. Sum of 1 says, hey, my sum is 1. I need to get the sum of 0 and add it in. And on the call with the 1, it finally calls sum 0, which we know is just going to say sum is 0, return 0. So on the call with 1, it says I'm already 1. Let's add in 0. And now I can return 1. And we go back to the call that had 2. In the call with 2, sum got initialized to what? 2, and the call to sum up numbers at 1 is 1. So it would say 2 plus equals 1 is 3. Let me return 3. And the call with 3 says, hey, my sum is 3. What is the sum of all of the numbers starting with 2? And we know that just returned 3. So it said 3 plus 3 is 6, and I return 6. And we get the same answer here. Whoops. What do I have here? 3 plus... 3 plus 2, let sum equal 2. Yeah. Thank you. So something changed here. So that's embarrassing, but it shows you, yeah, we have to kind of go slow with this. And I changed around 3 different ways that we could solve this problem. Just shows you that base case and recursive case, they're not always an if-else. We can kind of structure this however we want if we think about it one at a time. So start with the base case and then figure out what is your recursive case. What do you still have left to add? How do we feel about that? Which of those solutions do we like better? The if-else? Yeah. Yeah, so then go with the if-else. I just thought that this one line here, without having the variable, might trip you up as well. But generally, this is the style that I write it as, because that one is a little bit easier to calculate. What is the entire thing that I need to add up and not worry about updating the variable? Whichever you prefer. So then, just to show you more in real life, we're usually going to operate with data structures. So let's imagine that we're given a string and we want to reverse the string recursively. What is our base case? When do we have no work to do? Yeah, we could do 0 or 1 characters. Because if the string only has 1 character, what's the reverse of it? Itself. So, okay, let's do that as the base case. Let's say if string.length is less than equal to 1, what do we want to do? Yeah, we could just return it. There's only 1 character. There really is no reverse. And so let's test it.
Also, you can write it with in the reverse order too,
Yeah, we can write it any way that we want, as long as there's one path that will recurse and there's one that won't. It doesn't always have to be an if-else. They don't have to be in the same order. That's up to you. You just have to think about what's your base case, what's your recursive case, and how do we aggregate the totals? And how do we decrement? So let's think about it now. If I'm given AB, one, how do I recurse? How do I get smaller to hit this base case?
dot length minus 1.
Slice 0 minus 1.
Whoops. So when I'm figuring stuff out, this is what I do. Rather than test it in a whole big problem, let's just figure out the little code we need to basically make this string smaller. So instead, before we do that, if I'm reversing the string, what do I want to put at the start of my new string? Yeah, so we want to definitely start with whatever. If we're given AB, we want the B to come first, right? So that's we know that we're now returning B plus whatever. How do I grab everything besides that last character? So in this case, we're given AB, right? And we're basically handling the B. We want to move that to the front. So that means I want to reverse everything else. Or in other words, this. Maybe it's easier to see here. If we wanted to reverse this, really we want D plus the reverse of ABC, right? So now we're trying to figure out, if we have ABCD, how can I grab just this?
Slice this 0 and minus 1.
Whoops. Sorry. Yes, there you go. So what we're saying is let's make it smaller by let's pluck off 1 character and put it at the start. And if we know that that character is handled, we want to reverse everything else. So we give the next argument as the remaining characters. And we just figured out how to get the remaining characters here. So what do I want to do with this formula?
Call the reverse string function again. On that formula.
And so we test this immediately with 1 bigger than the base case. So we knew it worked for just 1 character. It works for 2 characters. Does it work for many characters? Looks like it does. So the questions that we had to answer to solve this are, 1, what is my base case? 2, how do I process one little piece of this? In our sum problem, it meant that we need to add that number into the sum. However we chose to do that, we needed to add the number to the sum. And then it meant, what else do we still have to calculate? And it's like, well, we got to get smaller to hit the base case, right? So we need to give a smaller input to the next call. So in this case, it's giving it a smaller string. And so that's a problem. We're like, how do we get a smaller string? So a good thing is to solve that completely separately over here, rather than in the middle of this big recursive problem, because that's tough. So when you're in workshop, or even when we take the CodePen test, if you're trying to just figure something out, like how do I grab all of the characters besides the last one, open it up in REPL or in Chrome Console or whatever, build a string and just work with the string to get that formula that took us a few tries. Because it's way easier to make sure that code works and to plug it into this recursive problem than to debug this whole problem when you're not sure if you're making a string smaller. Does that make sense? So once we figured out how to make the string smaller, then it was like, okay, that's what we still need to reverse. So we go in the recursive case here. Okay, so let's first start small with an array that's only going to be numbers. And let's sum up all of the numbers inside of this array. So we want to do this one recursively, which means that we want to get smaller and smaller, like the array size. So in the example that I'm saying for this one is, let's basically let our base case be when we only have one thing inside of the array, or nothing inside of the array. Okay, let's let the base case be when the array is empty. How about that? So let's make an argument where we have an empty array. And we want to return the sum of everything inside of that array. What can we do? So I don't want an array, I want some sum, right? So if there's nothing to sum, what do we want to return? Else, what can we return? How do we, one, process some work? We want to make this array smaller, and we want to add up one of the numbers, right? So what can we do? So let's not do splice because it's complicated. How about we just pluck one thing out, either from the front or the end? What's that? So we want to pop out a number, whatever it is, we want that summed up. So we'll have it in our calculation here. What else do we have to do? We know we now have a smaller array, and we're writing a function that takes in an array and sums up one number at a time. So what do we want to use? And in this case, what do I give it as an argument? The array, right? We've already handled making the array smaller. So this one, again, looks a little bit differently, but we had to answer the same questions. How do I process a single unit? In this case, let's pop out a number and let's add it together. And that will also make it smaller for us to go on the next round. So if we sum up an empty array, we get back 0. If we sum up an array that has one number inside of it, we get back 1. And 1, 2, 3 also works. Does that start to make sense that we see the similar patterns here and how the returns work? A little bit better? Okay, then let's do the final hardest one, and then we'll discuss if we want to hop to workshop or look at slides.
In the previous case with the array, it automatically returns a number.
That was your idea. You said, if the array is empty, let's return 0.
Oh, because
Right?
0 is a number, right?
Yeah. So we're just assuming, yeah, everything we pop out has to be a number just to make these make sense. And so, yeah, by popping it out, we get a number. The array is also smaller, so then we need to sum up everything that's still left. Now, this one was purposely trying to do recursion without a for loop, but in this case, what we want to do is we want to be able to sum up all of the numbers in an array. And we also want to be able to sum up all the numbers inside of other arrays. So let's say instead that our base case is just a flat array, an array of numbers. How would that look? Can we make this function sum up all the numbers inside of nums? Not that, because that's purposely going recursive at like a flat level, but here I'm saying we don't have to do that. We know that, how can we access every number in nums? What? For loop. So what do we have to do here? What do I need to store? What? We're not there yet. I need to aggregate everything, right? So we need a sum. We're going to return sum. What do we have to do in here? What's good practice inside of for loops? What do we want to do with that index? And what do we want to do with that current element?
Check if it has an array inside.
So we're not there yet, but you are correct. So we're pretending that right now it's just a flat array because we always want to solve the simplest case first. It makes it easier for our heads to do the inception. So here, we're just taking the current and we're adding it to the sum. And this works. We loop over all the numbers, we grab out the current, we add it to the sum. No questions on that, right? This is review. So now, we add in one array in the middle, and we test it again, and some really weird stuff happens under the hood. That's not the answer we're looking for. So what is our problem here?
Check our array.
So this is also a good idea when we're doing recursion to log out the current thing you're processing so it's a little bit easier to debug and figure out what went wrong. So we see that we added this array and we didn't want to add that array. But we just tested and wrote a function that takes in an array of numbers and sums them up. So if we find an array, what do we want to do?
Need to go again.
Yeah, so now really, in this for loop, what are our base case and what are our recursive cases?
Actually, we don't have a space.
Yeah, I mean, base case is basically, base case just means we didn't need to recurse. So in this case, if we pluck out a 1, we don't need to recurse. If we pluck out a 2, we don't need to recurse.
So if it's array dot is right. So if it's not, if it's
The length of our
So this is easier than length or anything like that. If our what is an array.
Current only.
So again, a little bit easier for us to first solve the base case. So let's just fix this, that we only add the current if it's not an array. And let's just test that and make sure that that still works. And it does. So now, when our current is an array, we just saw that we have a function that takes an array and sums it up. So what do I want to do here in the recursive case? What do I want to do? Just like that? Okay, so let's think about it. Multi-dim sum, I give it an array. And what does it give me back? It gives me back a sum of everything inside that array. So I probably need to do something with it, right? What do I need to do? We've already handled that if we give this function a flat array, it sums it up and it gives back the sum. So if I call this function with an array, it gives me back what? A sum, and I need to do what with that? That's it. So now, it still works, no matter how crazy we get. Just says, hey, I have an array, I need to go deeper. I have an array, I go deeper and deeper and deeper until this one finally got a 10. And it returned that 10 to some call that was waiting and said, add that to my sum, and return that to whoever called me. And so they all bubble all the way back up. This right here is basically as hard as we need to go with recursion. And I've told you 5 times, this is the interview question. And I think it's on one of the actual admissions assessments, not the one we'll take here. But it'll get asked in the interview regardless. And this one looks different than a few of the ones before because we still have a for loop. You can still have for loops in recursion. And we still have a base case and a recursive case. It just looks differently. Questions? Okay, I think we'll just break to workshop, but let's just take quick glances and see if there was anything in here. So generally, you see recursion instead of iteration only when recursion is actually easier to reason about. We saw that recursion can get pretty complex. So that's why if you don't need recursion, you generally shouldn't add it in if you don't need it, because it does get complex. But sometimes it makes what would be an iterative solution, it does make it easier. Because imagine trying to do that multi-dimensional summing up of like 3 nested arrays with a bunch of for loops. Like if we said it can only go 3 levels deep, you have a crazy amount of for loops and nested code, and that's actually harder to reason about than what we just saw. And we have to consider that it won't affect performance too much, but you'll learn that later on. For now, you'll know when you need a recursive solution. It's usually they're going to spell it out for you that we want you to do recursion, or it's going to involve like a data structure like an array where it could have unlimited arrays inside. And generally, in that type of case, your recursion is going to look like, hey, if this property is an object, I need to recurse that object. If this element of an array is an array, I need to recurse that array. And that's generally going to be your recursive in your base case there. And that's often the best use of recursion, is to iterate over objects with nested objects or iterate over arrays with nested arrays. Reversing a string just for the sake of it in recursion isn't really that useful in real life, but it's just practice problems. So it's also, yeah, someone said this the other day, it's good for machine learning, or same with memoization, and AI as well. So we saw the call stack. I think we're good on this. We saw a basic countdown. We saw more call stack here. So I'll review, right? Shake your heads if you're getting it, because I just want to make sure that we look at the slides so you don't think I cheated you, but I feel bad that we took a bunch of time. So this is all stuff that we did. And basically they show the infinite countdown loop here as well, because there is no what in this example. There's no base case. We need to say, hey, we don't always want to call a countdown. So all we did is separate a base case and a recursive case. Do we feel better about this one now? Start of the day is now easier. Cool. Yeah, 2 takeaways. You need to define a base case. You need to figure out how to separate the base and the recursive case. And the number one rule is the recursive case must get you closer to the base case. You have to find some way to decrement. So with strings, what did we do? Yeah, we made the string smaller. With arrays, we basically processed one element and then looked at the rest of them. In one case, we used a pop to just passing the whole array. And in the other case, we actually did a for loop, but we made progress as we went. And so, yeah, we saw recursion becomes more complicated when we need to return a value, which is why it's easier to start out with just the base case and figure out what am I returning when I don't really have any work to do. And then it gets easier to figure out, okay, if I do one more size than the base case, what can I return here? So this is why I skipped the slides, because the example we use to return values is factorial. So instead of summing up all of the numbers, it's based on doing a factorial. And the problem with this one is that it's too math-based. The trick here is that 0 or 1 are your base case, because apparently the factorial of 0 is 1. But at least one demo here is if you're ever stuck with the recursive problem, literally write out what the base case is, what you want to return, and then what like the next cases are. Because here you can start to see a pattern. If it doesn't immediately come to you, write out a few examples, because that'll help you patternize it to figure out what that formula was, like add the number plus factorial number minus 1. Does that make sense? So here is the code for factorial when they handle the base case first. Good. And here's where they took writing out all the math to figure out, hey, this is what I'm actually looking for. And especially when we're starting out with recursion, you can use a pen and paper to really figure it out in your head rather than just jump into code. So now we basically see the pattern is here to take the current number and multiply it by factorial num minus 1. And that's a pattern we did a few times today. Over here. But factorial is a really shitty example to give to beginners because it's too based in math. But here we have the call stack, just another visualization of what we wrote. Does this kind of click with you that you know what you're looking at here and the call stack makes sense? This one's paused, saying I need to return 5 times whatever the factorial of 5 minus 1 basically is. And this is how it builds up. And when this one finally returns a 1, this is how it gets passed all the way down. Does that help? So always write the base case first and test it with the base case. Then test it with the simplest recursive case possible, because it's way easier to debug your code and validate it than to do some crazy 10-level deep array. So it's most often used to recurse with any data type. I mean, they're saying you can recurse any data type, and problems will specifically say do this for arrays or strings, which will generally be a base case when they're what? When that data structure is empty, you have no more characters to reverse, or you have no more numbers in an array to sum. So we can't emphasize enough, start with the base case, then test recursive case with simple inputs and outputs. And if we need to return values, we need to figure that out ahead of time. So in the case of a sum, we probably need to return a number. So then in our base case, what is a good number to return if we have no work to do? And for us, that was 0. But in factorial problem, it's 1, and that's annoying. So if you get stuck on a recursive problem, sometimes it helps to write it with the while loop or the for loop and try to figure out which pieces of that while loop translate. Such as in our while loop, we're always decrementing the number. So that's probably what we need to pass to the recursive case. And that's it for the slides. Cool. Questions? Cool. Let's just get right to it.